Take a look at this clip from the 1982 film Missing.
As the Colonel suggested, if Charles was possibly injured, he could be in a coma or suffering from amnesia, or... Have you checked the hospitals?
I have checked some of them, yes.
Why not all?
This might seem like an ordinary conversation, and it is. There's certainly nothing wrong with it, but it hides a simple question about language which is surprisingly difficult to answer, more so when including the fact that it's so intuitive. Let's watch that again.
Have you checked the hospitals?
I have checked some of them, yes.
Why not all?
Why not all of them? The ambassador asks. When Phil says he checked some of the hospitals, the ambassador seems to understand he also meant he didn't check all of them. But why does some mean not all? This is one of the basic questions within a field of linguistics called pragmatics. Pragmatics is the study of meaning within context, beyond the basic meaning of each word and how they combine, which is usually reserved for semantics. Semantics and pragmatics both use tools from logic and set theory to form theories regarding meaning in human language. Well, that's just what some means, I might hear you say, and that's a perfectly valid hypothesis, which claims that this extra not all meaning is part of the basic semantic meaning of some. You can test it with negation. The sentence, "It's not true that Phil checked some of the hospitals," intuitively means that Phil didn't check any hospitals at all. Moreover, if Phil checked all of the hospitals, then this is obviously not true. But assuming some simply means some and not all, we get a different result, which is true if Phil checked either none of the hospitals or all of them. The same thing happens with numbers. 2 generally means not 3, not 4, etc. But take a sentence like, "Every kid who ate 2 cookies also drank a glass of milk." Obviously, if some kid ate 3 cookies, he also had a glass of milk. Under these definitions, we would denote the meaning of our sentence something like this. Every kid who ate 2 or more cookies drank a glass of milk. However, under the assumption that 2 trivially means 2 but not 3, we get a meaning like this, which only claims that the kids who ate precisely 2 cookies drank a glass of milk as well. And these cases provide some pretty strong evidence that this extra not more meaning is computed at the sentence level, rather than it being part of the word itself. This is what linguists call an implicature, an additional proposition made by the speaker and inferred by the listener without it being explicitly said. We use implicatures all the time while speaking, without even realizing it, because they are mostly really intuitive to us. However, the process behind them isn't so simple most of the time. There are many different types of implicatures. This specific kind is called a scalar implicature, because the different alternatives to what's been said sit on some scale, called the Horn scale, and making a statement about one item on it derives additional meaning regarding others. So how does it work? As an early attempt, Paul Grice introduced his 4 maxims of conversation, which act as unwritten laws for human speech, and they are in principle quite intuitive. The maxim of quality, the maxim of quantity, the maxim of manner, and the maxim of relation. These 2 are the most relevant to our case. The general idea is that people convey as much information as they can give honestly. Information isn't necessarily how many words you say, but rather how specific you're being. If we go back to our Horn scale, we can see what this means. Some means some. It could be all, it could be most, it could be half, it could be just a couple. We don't know. All we know is that John ate some amount of cookies. However, if we say all, we know specifically that John ate all of the cookies. The connection between these items are logical entailments. All necessarily means most, which necessarily means some, but not the other way around. Since all necessarily means most, it is strictly more specific, and therefore more informative. In general, a proposition P is strictly stronger or more informative than a proposition Q if P entails Q. So the basic theory is that according to the maxim of quantity, if the speaker meant all, which is strictly stronger than some, he would have said that. And so since the speaker didn't say all, he meant it's not true, giving some but not all. All isn't the only proposition which is strictly stronger than some, since some just means some amount, not specifying if it is all or not. Some but not all is also a strictly stronger proposition. And so by the same logic, we can create a parallel scale, and since the speaker didn't say some but not all, they meant it's not true, giving all. Obviously, the same sentence can't have 2 opposite meanings. This is called the symmetry problem, since some has 2 parallel strictly stronger alternatives that give opposite meanings. Its consequence is that not all alternatives are relevant when computing an implicature. In some cases, the relevant alternatives are a bit more clear. In some cases, a bit less, and they can change depending on the context.
Knowing the relevant alternatives for everything is hard, so let's just assume that we have some magic function, alt, that gives us the right ones. And so in stating John ate some of the cookies, we can also look at that statement's alternatives, when plugging in sum's alternatives. Our previous logic still works. The speaker didn't say John ate most of the cookies or John ate all of the cookies, and so we infer that it isn't true. This is the same as we've done before, but maybe a bit hand-wavily, avoiding the symmetry problem. But remember what happens with negation. If we say John didn't eat some of the cookies, it just means that he didn't eat any cookies at all. By this logic, if we negate the higher alternatives of a sentence, we get that he did eat all the cookies, which obviously isn't true. This is because under negation, the order of entailment is flipped. In the positive case, the sentence with all entails the sentence with most, which entails the sentence with some. But in this case, if John didn't eat some of the cookies, it entails that he definitely didn't eat most or all of them. This means that the sentence with some is now the strongest, most informative alternative, since it logically entails the others, and so technically there's nothing that isn't said and there is no implicature to derive. If the speaker would have said John ate most of the cookies, we would derive from the stronger alternative that he did in fact eat some, just not most, which is what we would expect. These cases are named downward entailing environments, because inserting alternatives of a lexical item on a scale causes the whole sentence to entail the opposite or downward direction of that scale. Similarly, these are upward entailing environments. In general, we can see that what's important is not the order of the scale itself, but the entailment relations between the whole sentence's alternatives, and so the implicature is derived only from the stronger alternatives of the said sentence. In a similar manner, Jake scored 6 points entails that Jake scored 5 points, which entails that Jake scored 4 points. Quantifiers can also be downward entailing environments. If every player that scored 4 points gets a prize, then necessarily every player that scored 5 points gets a prize, since he did score 4, and the same goes for 6 and 7 and 8 and so on. And notice how if I say every player that scored 5 points gets a prize, it's true for every player that scored 6, but I also understand that it's not true for every player that scored 4. This is also a scalar implicature. We can formalize this mathematically. Given a sentence P containing some scalar item x, like sum, we can compute its alternatives by plugging in the alternatives of that item, like most and all and sum itself. The meaning that it is derived is of course the original purely semantic or logical meaning of the sentence, called the prejacent, together with the implicatures, which are the negation of all the strictly stronger alternatives of that sentence. This symbol just means the conjunction or the AND operator on all these propositions together. This resulting total meaning is sometimes denoted as this exhaust operator acting on the prejacent. We have one more interesting case left, the case of disjunction, or. From a sentence like, Mary ate an apple or a banana, we understand that she didn't eat both an apple and a banana. This is an implicature since logically, or would still be true if she ate both. Or's alternatives are slightly less straightforward since they don't sit on a neat scale like the other two. But rather, we have good reason to believe that the alternatives of a disjunctive item like A or B are A or B, A, B, and A and B. We can map them not on a linear scale, but in this diamond shape. A and B entail A and entail B, both of which entail A or B. A and B are generally independent, and so don't have a line between them going either way. We can now try to use our formula to compute the scalar implicature for the sentence. Our alternatives are Mary ate an apple or a banana, Mary ate an apple, Mary ate a banana, and Mary ate an apple and a banana. Our formula tells us to negate all strictly strong alternatives, so Mary didn't eat both an apple and a banana, she didn't eat an apple, and she didn't eat a banana. This is of course a contradiction. Mary can't both eat an apple or a banana, and do not eat an apple and not eat a banana. Let's take a quick look again at the maximum quality. There's a reason it's be truthful instead of tell the truth. People naturally don't know everything. If everyone knew everything, human conversation would be kind of redundant. So what it basically means is, only say what you know for sure is true. And therefore, if someone didn't say something, assuming it's relevant, they either know it's false, which is what we've assumed so far, or they're not sure about it. Now we can go back to our diagram. We know the speaker said that Mary ate an apple or a banana. She didn't say the other three alternatives, so we infer that they either don't know if they're true, or they know they're not true. But they can't all be true, because otherwise the speaker would have said it. Let's look at our options and try to negate as much as we can, to derive as much information as possible. Remember, since the speaker didn't say these alternatives, then they either know them to be false, or they aren't sure. They can't knowingly be true, because then the speaker would have said them. We start from the option that A is false. Mary didn't eat an apple. A and B therefore must be false to be consistent with A being false. We can negate B as well, because that would contradict the first statement, leaving us with this maximal set of negated alternatives, consistent with the prejacent. We can also take a parallel set of negated alternatives, taking B to be false and also A and B, but not A, since that would create a contradiction. These are all our options, assuming the speaker isn't sure whether the stronger alternatives are true. However, we can see that in all these cases, A and B must be false, and so we can be sure that at the very least, Mary didn't eat both an apple and a banana, while not being sure which one she did eat. This proposition is called innocently excludable, because it can be excluded from the intended meaning while remaining innocent about the other alternative's truthness. These remaining alternatives are derived as what's called ignorance inferences, since the speaker is ignorant about their truthness. The final meaning looks like this. This K operator can be thought of as I'm sure that, and so not K means I'm not sure that. To formalize this algorithm, we'll need just one extra definition. A maximal subset A prime of a set A under a condition capital P is a subset of A that fulfills P and cannot be added to while still fulfilling P. That is, every other subset which contains it violates P. Notice how there isn't necessarily just one of these. Think of the two options from before. They both fulfill the condition of not forming a contradiction with the prejacent, and they both can't be added to, while still fulfilling that condition. We can now go back and formalize this algorithm. Given a prejacent P, we generate a set of strictly stronger alternatives C. We construct subset C' that are maximal subsets of the stronger alternatives with the requirement that their negation is consistent with each other and with the prejacent. The intersection of these subsets is the set of innocently excludable propositions, since it is the set of propositions that must be false in all cases according to the maximum quality. We can thus knowingly negate them, and the rest are left for ignorance inferences. I'll also point out, and you can prove this by yourself, that if the alternative to the prejacent are a scale, like sum, most, and all, we get that the set of innocently excludable propositions is just equal to the set of stronger alternatives, and so they are all negated, and we get the same meaning we got from the previous theory. Now this is just the tip of the iceberg. This whole thing is far from being a complete theory of scalar implicatures, and it just goes to show how human language is so much more complex than we realize, and also how math can be applied to just about anything.